Thank you everybody for being here. Everybody who is physically here and made it to actually the lecture hall, and everybody who's watching from far away. I figured out after many years that I kind of learned a lot about technology over the years, but I was struggling with conflicts that arose from technology. And so I thought, in order to learn more about it and maybe improve my understanding and unskillful activities on that front, the best way to do it is to try to give a talk and see if that can teach me something. So if you look at the talk from the perspective of an attempt to learn more about the subject, it may explain some of the things that are in there. So in order to start, I really need to start way back, because this is also the picture up on the talk announcement. This is really the guy who's got me here. It's me from 1982, which is when I decided that computers are cool and I would like to build the world's fastest computers. And that kind of set me off on a journey that was very interesting and continues to be interesting now. But I thought to give some credit to the person who got me here, because it's a completely different person from me today. Although we share one thing, which is we both really enjoy doing assembly programming. And so this is how it all started. And just today, I had the tremendous honor to meet somebody who was part of the Zilog team that built the Zilog Z80 that was in that computer. So that's kind of was a surprise for me this morning. So this is how it all started with sequential instructions. Some of them had to be hand-coded, of course, and had to translate these things into zeros and ones and then feed it into memory by hand so that it would go in. So it was a bit tedious, but it did pay off, because it led to an amazing EE380 lecture that I gave some years after that. So the next step, I'm fast forwarding here. Obviously, there were a few steps in between, but this is 2001, where I gave a talk here at the EE380 seminar on this crazy idea I had, where you could build faster computer than anything else. You could build the world's fastest computers out of these chips called FPGAs. And there's a lot of credit to a lot of people who have, of course, helped and influenced that, many of which are also in this audience here. But the idea was not the whole thing. There was the second part, which is to actually make it happen. Going from the idea that something is possible to actually deliver a complete working system in production in a place that is using it and measurably benefits from having that speed and that activity happen in a different computing environment than the world is used to. So this was the talk, and I'm not going to go through all of it, but it basically says FPGAs can outperform microprocessors on certain tasks by many orders of magnitude. That was kind of the premise. I kind of thought, yes, I think that should be possible. It was a big leap, because it was not clear that it can be done, but it looked like it should be possible, and there were people like Dennis Ellison, of course, Martin Morf, and others who were encouraging me in that direction, saying it should be possible. So after that, the next step, this is again a few years later, you go 1 decade on. I'm really fast forwarding here. There was a credit crisis, and during the credit crisis, people wanted to compete from credit derivatives. And so we had JP Morgan, the largest bank in the Western world, come here to Stanford to give a talk at EE 380, exactly 10 years after the first one. And they were talking about the deployment of a machine built by the company I started to do this, which was computing scenarios of risk calculations, what could happen in the future, so that they can balance their portfolios and make sure the whole thing doesn't go under. At the time, this was publicized as reducing their compute time from 8 hours down to 2 minutes. So it made a real operational difference. Instead of waiting all night to get the computation done, they were saying, now we can run it in the afternoon. Now, of course, the people who were running the data center that was running all night, they were not happy at all, because the computation was supposed to run all night and they were supposed to take care of it. And if it can be done in 2 minutes in the afternoon, there is really nothing for them to do all night watching the computers to do something. So what I didn't expect at this point was that anybody would have a problem with that. It seemed to me as if the problem was there, I've solved the problem, everybody should be happy. And yet, a lot of people were extremely unhappy. And that came as a surprise, and it took many, many years for me to catch up with that surprise, that I've done my homework, I've submitted my answer, the answer was correct, it was accepted as working, everything's good, I get a good grade and get a degree. But no, in this case, that didn't happen. And so that's what led me onto this new journey of what happens when you actually do these things. Now, we were pushing it a little bit further after that, saying, well, what's the hardest thing you could possibly do? Well, von Neumann thought that weather prediction is the hardest thing, and he dedicated many, many years of his life to weather prediction and climate, and just thought that was the hardest thing you can do. So we have a climate model implemented here. We said, well, we wouldn't do it ourselves. Let somebody else do it. So this was done over at Tsinghua University in China by students there, and they used our infrastructure and the machine that they got from us. And they compared it, of course, to the world's fastest supercomputer that existed in China at the time. The result is here, published in a paper in 2013. It showed that it was running 14 times faster. So the first mistake people make is say, no, you mean 14% faster. It's like, no, it's not 14% faster. It is 14 times faster. So how can it be? It's the fastest computer in the world. How can it be 14 times faster than the fastest computer in the top #1 computer in the supercomputing list? Well, the answer is very simple. We were measuring the speed you can attain in a fixed amount of space and with a fixed amount of energy. And apparently that's not how you measure computers. You measure computers by saying who has the most money to buy the most computers to stick into the room, and then you say whoever's got more, he has the fastest computer in the world. So if you've got more money, you can buy more computers, and then you get to the top of the list. Any other kind of measurement apparently is not a valid measurement. That's not the right way to do it. That's how we could do it, by simply changing the metric, changing the way we're measuring. I thought, it should be really computations per watt that should matter. And we see, of course, per watt energy improvement is only 9x, because there's some inefficiencies, of course, in translating the speed to power. But we thought that was quite good. And there was a machine here that we built is a picture of an actual Maxeler computer standing in a data center next to an IBM Blue Gene. And there's another picture there of getting some attention on the world stage in terms of doing something that seems to be different from what anybody else is doing. So that was great. What was the next thing? We said, okay, fine, we need more applications. You need to have applications to run on these computers. So the European Union funded a project where we ported 4 of the top applications in HPC to this new machine model and paradigm. So we implemented starting bottom-up earthquake simulation. It's quite important for people. Quantum Espresso is a chemistry simulation that takes a very long time. NEMO is ocean modeling, very important to figure out how the currents are flowing and then what's happening in the ocean, especially now with global warming and the impact of climate and oceans and all of that. And then the one at the top, which is my favorite one, which is quantum chromodynamics, simulating the forces inside of the basic particles that form, that put the quarks together into the actual basic particles. So it's simulating quarks interacting with each other. Possibly the world's hardest simulation you can do, because that's at the bottom of the food chain. Any system you want to simulate will have the most quarks, regardless of what else is in there. And we showed some speed up, depending on how much effort we could put into that. But again, multiple times of performance that the competing systems would do. And each time there's a different type of computer that they told us they're currently running it on. So we're comparing it to the machine that was actually used by the scientists that they picked for that kind of problem. There is a cluster of blue gene Q. There was a comparison to the Cray XC30, another blue gene, and the Curie cluster, which is just regular CPU nodes like x86. So then let's look at the broader impact of what has this done to our suppliers. So we buy chips from a company called Xilinx. They make the FPGAs. And these have been picking up in the data center space and in computing quite a bit. We can see here what happened. First E380 talk was just after the bump of 2000. I started Maxeler when the stock price of Xilinx was quite at the low level. And not much happened really until the point we had Intel buy the main competitor of Xilinx, which was Altera. And they paid a lot of money for it. That gave a huge boost to the whole concept of computing with FPGAs. And then at some point later, we had a new CEO at Xilinx, and he announced a data center first strategy on Wall Street, which was the direction that the company was going to go from then on. And the stock price really kind of took off from there, with a little bump at the end where the US decided to suggest they would limit the sale of certain technologies to China. And that caused a dip in expectations of what that would be, because FPGAs may have been one of these technologies that could have been limited to be sold to China. So this is quite interesting as a development from saying in 2000, but certainly even in China, there was more focus on one organization in particular, I believe, that was in particular in the crosshairs of the government. Well, probably most of them.
Really?
So the biggest percentage of sales of these chips go to Huawei, and then is the rest of the world.
Okay. Interesting.
Yes?
Are you going to be in Denver in November? No, I'm serious. We can answer that question while we're in Denver.
Denver is the supercomputing conference, which I have been avoiding successfully for the last few decades. Yeah, that's a good topic for the dinner. Maybe not so relevant for the talk, but absolutely. No, so let's step out of this and see another slide, very interesting, from the CEO of Mentor Graphics, one of the leading US companies in silicon software tools. This is a slide from Wally Rines from a public slide deck that is on the internet. So I thought this is particularly interesting. It says that there is 2.8 times the investment into silicon technologies in China, fabless silicon technologies, compared to the US. And that is spoken by the CEO of the US company that just got bought by Siemens, which is a German company. Yes?
Does the U.S. Controls on exports also apply to the tools used for making chips? Like Mentors?
I am not aware of any limitations on software sales.
Actually, the answer is yes.
It does.
It
Okay.
applies to all technology.
Okay. Well, I'm not, as I said, this is not my expertise. So yes, happy to, yeah, there may be some things, don't know. So then at that point, that kind of brought me to the idea of really it's about conflict and how these conflicts are managed. I got here this little quote, which I thought was quite telling, where force persisted through a series of conflicts, then vanished. Yes, not with a bang, but with a whimper as the economic and social environment changed. And then new problems and a new series of wars, suggesting a cycle of conflicts. And that, of course, is from Isaac Asimov. What I didn't know, and Dennis kindly taught me that this morning, is that it comes from Isaac Asimov quoting T.S. Eliot. So it has a longer history of where it is coming from. So then that brought me to the conflicts, and you say, okay, where do we start? Well, if we start with the conflict between US and China, you then have other more mundane conflicts between chip technologies, as we've seen in the industry, conflicts between CPUs, GPUs, FPGAs, which one's the right one, which one's the better one, which ones should you use, all of these discussions. Then there is a conflict between VHDL people or Verilog people who write hardware circuitry in RTL, and high-level synthesis people who like to use higher-level languages, higher-level things to generate these. That has been a conflict going on for decades. Very, very harsh conflict, maybe even harsher than the ones about it. Then there's a conflict between software people and hardware people. Software people would say that everything should be done in software. The hardware people say, yes, but I can build one that's much better than the previous. So there's always two different perspectives. In the commercial world, you then have conflicts between internal and external, where you come and you want to actually deliver a technology to a large corporation. There's always a team in that large corporation that already has the job to do that. And it becomes very difficult to convince them that as an external group, you bring that thing into that organization. Especially for a small supplier, there is nothing in it for them. If you're a big supplier, buying something from a big supplier is always very good for people's careers. While buying something from a small supplier, that's a real problem for social and economic environments. Then in the banking environment, one of the things that we realized with working with financial institutions is the discrepancy of expectations between people who are trading and running P&Ls and making the money, and then the back office IT people, the people who run the machines behind them. And that's an internal thing that is happening in these organizations, but working with them, one finds itself either on the one side or on the other side. You kind of have to pick sides. And I thought, I don't want to pick sides. I'm not interested in that. I just built this computer. It runs fast. I can enjoy that. But that's not possible. So you get dragged into these existing conflicts. If you want to, you don't. There's, of course, always conflicts between employees and management, and you can easily check the comments about myself on Glassdoor to get a good feeling about me and what I'm doing. They're particularly entertaining, so I really encourage everybody to do that. The small and large companies, obviously, there is the not invented here syndrome, the change due to new products, inertia, all of these good things. But most importantly, and something that I found fascinating, is there is this conflict between old conflicts and new conflicts. You have things that have been a conflict for a long time, been around, but then there are newcomers, things that we didn't know existed, things that that just came up, and you get surprised by them saying, oh yeah, another one. Like populism. I keep trying to tell people I didn't know the word populism 10 years ago. I didn't use that. Nobody used it. It's a new thing. And suddenly it's a problem because they're the people who are against populism and the ones who are for populism. And we didn't have that. I don't remember a problem with populism before. There is a new problem where we now believe that the internet is bad for democracy. There's all these ways where the internet can be used to influence it and change things and impact elections. I'm not aware of that problem existing 30 years ago, 20 years ago, 10 years ago. It's a whole that you have to now think about. Say, what does that mean for my actions, for what I do and how I do it? Most shocking, I was just reading an article where there's a conflict between people who want to explore Mars and the people who care about global warming. Why would these people have a conflict with each other? How could that even happen? Well, the people who want to explore Mars, they want to take away money from the people who are worried about the global warming, who want to fix the planet, versus the ones who explore Mars who want to leave it, just go somewhere else. So these are two competing ideas now. And you have to pick sides. You have to say, oh, you're either one of leaver or a remainer, right? It's a crazy world. I didn't think of that at all until just a few weeks ago when I read this. So my first observation here, coming from an engineering background, is that the law of thermodynamics with entropy increasing or kind of staying the same in a static system applies here. It seems to me that from an individual perspective, for me as a human being, the number of conflicts that I am part of, that I see around me, that I'm participating in, seems to be increasing over time. It doesn't seem to be going away. So the number of conflicts we participate in seems to be going up. At the same time, we have, of course, the law of conservation of energy. My energy is not increasing. I have the same amount of energy that I had before, and I have no way to increase the amount of personal energy I have or the amount of time I have. What does that mean? It means that the amount of time and energy that I have to deal with each one of these conflicts is going down. Right? I don't have time and energy to deal with each one of them the same amount that I had before because there's so many more of them. I have to worry about them. Where am I standing? Where do I position myself inside of that? So it's getting a lot more complicated. There are some people who have already pointed out to me that sometimes conflicts get resolved, and that may be a kind of unsupportive element for my observation number one. So now I thought about it, I said, yes, it's true, some conflicts get resolved. So what do we do with them when they get resolved? Well, we quickly write them into a book, and we give the book to our children to read about them in school so that we don't lose them. So we're really hanging on our conflicts. We're not teaching people or children about great stuff that has happened 100 years ago. No, we teach them about conflict number 1, conflict number 2, conflict number 3, and they have to remember the years in which each one of these conflicts happened and who won, right? And depending on who wrote the book, of course, there's a different story. But we really don't want to give up on conflicts, even 1,000 years after they happened. Some people hold on to them for even longer. So there is a discussion, but I'm still holding on to the number of even if they get resolved in some way. Here's an interesting one. I was going to visit a potential client to just show the kind of perspective of you have this great idea and you go to someone, you tell them about this great idea. This was Knight Capital Group in New Jersey. They were, as it says here, the largest trader of something at some point in some way. And I went there and we told them about a great idea, a kill switch, a piece of technology you put into the network, and if you start losing money too quickly from your trading, if the money goes down, it makes mistakes, then the machine would simply cut the wire, stop it, so you don't keep sending these buy and sell things, so you kind of stop it, we have time to fix it. I thought that was quite a good idea. Seemed like a really important thing to do. These were people trading very quickly on the nanosecond level. So they really had a big risk of something going wrong. By the time you figure it out, it's already all gone. We did have over 100 people in the audience, and they all listened very carefully. And then the CTO came over to me, and he told us that we don't make any mistakes. I mean, if you think we make mistakes and then things happen, that couldn't be. Because if we were to make mistakes, he said, we wouldn't be around today. We have clearly not made any mistakes in the past. This has never happened. So predicting that it would happen in the future is based on past history, has never happened before. So why would we predict that it could happen in the future? Right? So it also says that of course, they ceased to trade on July 1, 2013. And so I have my calendar entry here in 2012 and the end of the existence of that organization in 2013, which is a fantastic story where they had a bug in their software, and a software programmer was told to fix the bug, and he fixed the bug, and he checked it in, and they turned it on. 2 seconds later, all the money was gone. The bug fixed the problem, but it also had some other side effect that meant that they lost all of their money within a few seconds. So the whole organization, thousands of people, just ceased to exist within one bug fix. And there was, of course, no kill switch there to stop it. So I thought that was quite a story to add. If we go back to this one, yet another one of these, I showed these pictures as examples of a great accomplishment, but I can also show them as examples of conflict. So the picture here on the left is now quite a few years ago, and of course you can imagine the number of conflicts that have arisen from the two parties in the picture if you follow boring European politics. There's also a conflict on the right. You see a Maxeler machine standing next to an IBM Blue Gene. And the conflict on the right may as well have been a lot more intense than the one on the left, because it was clearly a tremendous mistake of history that the Maxeler machine was ever allowed to sit next to an IBM Blue Gene right there. So these are conflicts that one doesn't think about. I wouldn't have thought about, where is my product going to sit and who's going to be next to that and who would be bothered by it. No, these are real, actual pictures. So as part of all of that, the amount of uncertainty seems to be increasing. The better we get at predicting the future, the more AI we use, the more we learn about how we can predict the future. The more of the future we are predicting away, the less predictable the future becomes, because we've already predicted away all the stuff that can be easily predicted. So the side effect of getting better at predicting the future is that it's getting harder and harder, and the future is becoming more and more chaotic. And we can see some of that in things happening where you say, wow, I wouldn't have thought that could happen. And more of these world events where you think, I would not have been able to predict that one, are happening around us. So, for example, can an AI today predict which company will be around a year from now? More importantly, if an AI was to predict which company will not be around a year from now, what does that do to the stock price of that company? Right? So these are just questions. I don't have answers to this, but I do have another observation to add here, which is following from the efficient markets theory. So the efficient markets theory is quite well known. Price is established by supply and demand, and you have an efficiency in there, which means that any knowledge about the future is priced in the current price of an asset, right? And if you apply that to my idea here, you can say that because of AI predicting the future is getting more and more unpredictable. Because the future gets priced into our understanding, it becomes our current present. And if the predictable future becomes our present, then there's only the unpredictable part left as our actual future. Just observations again. No hard proof possible at this point yet. But I'm now taking that to the next level of saying, okay, can we apply that to something useful, to something that we all want to do? It's always a pleasure here to speak at Stanford, because the audience in Stanford is extremely entrepreneurial, and all the students here are clearly going to want to start their own business. And so I thought maybe sharing a little bit something about how that looks like could be quite useful and fun. And so here is how I perceived the whole process is going. So you go to school, you're given a problem, you find a solution, the end, you're done. You get a grade, everything's fine. If you had it right, everything is good. Right? You had the right answer, the right solution, you solved the problem, you get trained to solve the problem. What you don't do is you never think about which conflicts would be created by the solution that you've suggested. That's beyond that. That just has, and so nobody ever thinks about that. We don't get trained to do it. We don't get taught. There's no books about this. There's no way to learn how to do this. And yet it happens. You have a pain point. You start a company. You find a solution. You build a product. You sell the product. You create all kinds of conflicts with that. And they hit you. You say, wow, I wouldn't have thought that that would be a problem. Because all of these conflicts, they all create a lot of pain points again. So you've started with one pain point, you end up with many. Even though you had the correct solution, you did everything right, the product does address the problem that you've addressed. And then even worse because if you come from a technical background, like technical stuff, you solve technical problems, you pick a technical pain point, you solve the technical pain point. What do you get in return? You get non-technical pain points back. So somebody doesn't like it. It's like, yeah, but it's the right answer. Technically, it works. The fact that somebody likes it or doesn't like it is not a technical problem, right? There's no course that I know of that would prepare you for that or help you with that, to think about it. Even less, any that would let you predict it. Because one of the things you would need to do is you would need to predict what that conflict is that your solution is going to create. And that's even worse because that's way beyond. So I thought of it from an engineering perspective. Of course, I see a state machine in everything I do. State machines are great because they're understandable from an engineering perspective. So here we have the start a company state machine, where you start with a pain point. You're told in lean product development, you start with the pain point, you find your solution, you build the product, you sell the product, you make some money. Great, you did that. But it's a state machine. What happens is, after you sell the product, you're creating conflicts. You may be creating technical pain points, commercial pain points, social pain points, or legal pain points. You may not know much about these different topics when you get started at the beginning, because you picked your own pain point as something that you really like. But many technical solutions end up with a legal issue that they haven't thought of, and they have to backtrack because they don't know how to solve that one. Or a social issue, or a commercial issue. So when you do a product plan, you need to identify the pain point, you need to identify the conflicts caused by the solution that you have, and then identify the new pain points that arise as a result of that. And the speed at which you can do that determines if your state machine is stable or unstable. Because that state machine also has a hold condition. As we know, all state machines, or some state machines, have hold conditions. This one has a hold condition, which is money goes down to zero. So if the state of your new enterprise is the bank account and the total amount of money you have in there, at the point when the money goes to zero, the state machine stops. It's just halt, finished, doesn't do anything anymore. So I found that quite interesting. Because it really looks like this, right? You sell the product, you create the conflicts, you find the pain points, you find solutions to these pain points. You may be really diligent and find the solutions, but that just creates a whole other range of conflicts. So you started with one pain point, it grows quite dramatically. And if you don't start preparing for this early, solving that one first pain point is irrelevant. You're going to find the solutions to these 16 problems that you've just created, right? If you can do that, then it's worthwhile to start solving the first one, which is easy. Anybody could have done that, right? It's just one, and it's technical. And if you go to a good school or you study hard, you learn, you know how to do things, you can learn how to solve a technical problem. The other ones are much less deterministic. So then going back to my endeavor of having built really, really fast computers, I thought that's great, it worked. We build it, you turn it on, it does exactly what I said it would do. Fantastic. Here's a list of conflicts it created on the first round. So that's not a few, that's quite a bit. So we ran into lots and lots of issues. One was, well, of course, we started with saying creating circuits is hard. Designing circuits is hard. Let's create a high-level language to do that. And we've done that and made it really, really easy to program these machines. But then we figure out, well, there's a side problem, which is when you buy the chip from the company, you need to connect memory to it, because just computing is not enough. It needs to come memory. And with that memory comes a memory interface, connection to these memories. And turns out that the company that makes FPGAs doesn't have as fast connections to memory as CPUs and GPUs have. So you start off with very slow connection to memory. You say, oh, that's not good. You got to solve that. That's an actual problem. There is floating point, which now doesn't work very well on these machines. Oh, okay. So if that doesn't work very well, got to do something else. Got to do fixed point or some other number representation. Now you have to study number representation. You need to know numerics. There's a solution to that one. We have to separate CPUs and FPGAs. Because you may need some of this and some of that, but you don't know how many of each you need in each instance. So putting them together means that you're inefficient in resource sharing. Application need to steal the source code from the person who's written it or from the person who owns it, carve it out of their dead fingers who are holding on to this to not give it away, and take it and then change it and give it back to them changed, which they won't want to have. Debugging the thing afterwards, really hard. How do you debug a circuit? It's not a software thing. There's no way to step through it. What are you going to do? It just kind of doesn't, then it's wrong. So debugging it, really, really difficult. So you need a whole other thing. And then you're left with the compiler. Just compile it. Yes, you compile it, but when you compile it, it takes 3 days. What? Well, it takes 3 days to compile the program to actually get the circuit out. And that's where people stop and say, well, wait, what? Who? Where? 3 days? Well, you push compile, and then what are you going to do? Well, you wait for 3 days until the software has actually mapped the thing onto a circuit and put it into the chip. That's a really, really big conflict caused, because on the other side, I'm just compiling and pushing the button. It compiles in a few minutes. Now, there is a special problem, which is that the people who know how to write these circuits, at the end of the day, if you do solve all of these, are out of a job. That causes unhappiness, even if everything works and even if you've resolved all of these. But then there is a 10th, even most annoying problem, which is that most software doesn't need to run any faster. Or it can be easily fixed in some other way. So the necessity of running computers faster is not always given. So there's solutions to these things. I'll walk you through quickly. We have a programming environment. There's a university program. Over 150 universities in the world are using this for playing around with creating circuits. There's publications for over a decade on doing these things. It's a dual representation inspired by Professor Morph here, who taught me about dual representations and drawing the graphs next to the text and doing that together. Lots of fun for the adventurous programmer. We have another fun thing where we can connect the area of the chip to the actual Java program you write. So you write a Java program, and it annotates for each line of code how much space it's going to take on the chip. So connecting space and time, which is a fun tool. And so we have many of these. You can annotate it also with time. So you could say this number of nanoseconds for this line, that number of nanoseconds for the other line. So you can both optimize nanosecond latency for a computation, as well as the space it is taking on the chip by looking at the different Java statements, very high-level statements of flow of data. So this is solving the idea of making it easier to program in that space. The memory interfaces, what do you do? Well, there's 4 solutions we found. The memory interface is slower. Okay, fine. But there is a memory on the chip, and that memory has more than 10 terabytes per second bandwidth. Let's use that one. But it's smaller. Okay, so you need to partition your application into smaller pieces that fit in the 10 megabytes or 20 megabytes that you have in the chip. And then you use 10 terabytes per second, which is a lot faster than any other technology out there for accessing memory. So you can do that. You can also build cards with a lot more of that memory on it. Turns out these faster memories also cause a lot of problems electrically in terms of cooling it and space and all of that. So we were able to put 96 gigabytes of DRAM onto a little card that was half the size of a GPU card that had 8 gigabytes at the time. So, wow, okay, so you can hold bigger problem sizes. Of course, then we would say, well, we can solve problems that are much bigger than the GPUs, because if your problem fits into 96 gigabytes, it's a home run compared to GPUs, which have to talk to all kind of other cards, and you have inter-card communication. Of course, then people would say, fine, but I'll just compute the small problem. Maybe I don't need the bigger one. It's not so urgent. You have new things coming out. Acronix is a smaller FPGA company now coming out with a fantastic technology, including GDDR6, which is the memory technology that the GPUs have. So you can now get that combined, which was not available for many years. And of course, Xilinx also has a solution to this, which is the metrical one, which is to use HBM. You have a package, and you put the DRAM into the same package together with the FPGA. So now you have an FPGA with DRAM in the same package, ultra fast, very efficient, really nice solution to this problem. So there are solutions to this, technical solutions for floating point. We redeveloped the whole idea of computation around different bit widths. So every variable in your program could have a different number of bits to represent it. And so we have a numerics tool that lets you plot and analyze and understand the numerical behavior of each one of your variables. Turns out some people get offended when you tell them that a variable has a statistical distribution of values that it takes across the lifetime of the program running, because there is no science behind that. There is no math that can explain to you what that means. Because in math, of course, all variables have infinite precision and are always perfectly accurate. And the solution to the numerics problem is to make everything a double precision floating point, close your eyes, cross your fingers, and hope for the best. Right? That's the mathematician's solution. The physicist is curiously interested in the topic, but doesn't have any mathematical tools to study them at all, because the fact that a variable would have a finite precision doesn't have a mathematical theory behind it. So graphically it works, and so we have a tool, and you can look at it, and you can study the statistics and how many bits are needed. Separating FPGAs from CPUs, we had to build our own machine. So we built a box which has FPGAs in them connected with InfiniBand. And now you have the FPGAs outside of the CPU. What does that mean? It means that the computation moves away from your CPU into the other box that doesn't have the CPUs. Now, that creates an obvious conflict with server vendors who say, well, we sell CPU servers. You're saying you're taking away the computation from our box and you're putting it in your box? That's out of question. I mean, you can't possibly say that that's what you're going to do. You're going to do the computation in the box. You may be able to send a little bit of stuff across the PCI Express bus to something else, but you can't take the whole computation out and put it in the other box. I mean, that's just out of question, right? Commercially, that would mean that you lose the computation to this other box. Another conflict we ran into was a strange one, which is that we used InfiniBand, which is a networking protocol to connect cables. You go to a bank, you say, we have this thing and it does this. You say, okay, we'll get one. And it connects these boxes with InfiniBand. What? InfiniBand? No, you can't have that. InfiniBand is forbidden in banking data centers. Say, what? You have a rule against a networking standard in a data center, especially the fastest one that is out there. Why would you do that? Of course, you can't get any answers to these questions, but we say, okay, fine. We'll rename it. We'll say, this is a Maxeler interface. And
banks still using binary coded decimal. Of course.
The answer to binary coded decimal in banks is yes, but exclusively on IBM mainframes, which are powered by COBOL. So it would not be done in any other programming language. So it's only COBOL and only on IBM mainframes. But yes, our world still lives on IBM mainframes and COBOL. In fact, possibly all of our bank accounts are stored on an IBM mainframe in COBOL.
There are a few in assembly still in banking systems.
Okay, well, I'm sure there are, because nobody would dare touch any assembly language. That's right, yes. I'm sure there is. No, there's always exception. I'm not saying all of it, but big amounts. There was no software, so we created a software store, a software gallery for FPGAs. We have a nice number of applications on there. Need to rewrite parts of the application. Well, okay, fine. So we developed a corporate process of rewriting software, of analyzing it, figuring out which parts to rewrite, and teaching people how to do that. There's a new conflict we created there because we're changing the code, which is maintained by someone, which is now only compilable with a proprietary third-party tool on proprietary third-party hardware. So turned out people don't like that. That was kind of sad. But then NVIDIA came along and convinced the world that it is okay to rewrite parts of your application in CUDA. And after people started rewriting things in CUDA, that argument went away. It was okay to rewrite things because they've just done it for CUDA, so it's possible. So that was solved by that activity. And of course, there are some automatic compilation things, like there is a big stream nowadays that offers automatic use of FPGAs for standard software packages. FPGA debugging is hard, so we have debuggers that check where the numbers are, how they flow through the system, what happens to them. So you get visibility into the hardware as it is computing, and that helps with debug. That has, of course, issues also on efficiency. So this is a tool that shows events across multiple nodes, multiple chips, multiple activities, and you want to be able to overlap and balance computation across multiple chips, CPUs, FPGAs, others. And so there's a tool to do that. And there is one that looks at performance between different kernels on the chip, how the data moves, and helps us to debug performance issues if it doesn't run as fast as it should. Then you can monitor that with with something that shows you the runtimes of the different kernels. But we still have the problem of place and route taking 3 days. What are we going to do about that? Well, we thought, first, let's build a large cluster of machines and have a job distribution system for these compile jobs. And so we built large amounts of infrastructure, tools and hardware to do these compile jobs. And that meant we have to have a little data center in the office that we have to play with. Fair enough. Then we said, okay, fine, maybe we could go to the FPGA vendors and tell them this is a problem because maybe they haven't thought of it. So say, well, why don't we take the source code for place and route and we accelerate it on the FPGAs? And all the conflicts I have mentioned so far in this talk are nothing compared to the conflict that has been created with that suggestion. Because of course the software for place and route is the holy grail of the FPGA community, and they would never ever let anybody touch it, let alone put it onto an FPGA. That would be completely outrageous and unheard of. So didn't get anywhere with that one. But there is another solution as well, which could help. Not that we made any progress on that, but one could change the architecture of the chip as well in order to be easier to route if one gets rid of the timing closure problem. So if you just put in the flip-flops, you run it at the fixed clock frequency, you would solve it as well. But again, that's a bigger solution out there. Finally, how do we help people who really like hardware descriptions? Well, we gave up after a decade and a half of trying to convince people that they shouldn't be wasting their time writing circuits on the RTL level. We now have a solution for it. You can just use our tools to generate IP cores in RTL, and then you can use it and you don't need to tell anyone that you've used our tools to generate it. And then if you can generate something with our tools in a day that would take you a month or a year to write in RTL, that should have some benefits. So there's now a way to interface between hardware activities and the tool set that we have. We also have a way to import these IP cores. If you write your own HDL bit and you say, I'm happy to use the new tools, but I have this thing I wrote 10 years ago and I really can't give up on it. This is my favorite circuit. I will never be able to do anything without it. You can now import it into this system as well. Finally, one of the annoying ones, most software doesn't need to be accelerated with special hardware. Here is an example of a proper production code used for regulatory reporting, which is very important. This is when you report to the government something that is legally required for you to report to them in a timely manner. And they said, well, this has to be reported in a fixed amount of time. You have 8 hours from the request to report it, and this thing would run for 3 days. So they said, wow, you've got to build some special hardware to do this. We looked at it, and it was an SQL script. They said, but this SQL script is really fast. I mean, this is an SQL script that by the world's leading vendor of databases has been made to run as fast as possible. And we have the fastest data. We wrote it in Python, and it ran 119 times faster. Okay. So special hardware is not always necessary. A little bit of proper knowledge of computer system helps as well to solve many of the world's problems. But again, it's something that comes out of it. To explain it, they didn't believe it. So we had an analogy to explain it. I drive a Prius when I go to the airport, and I said, well, the equivalent, if you think the Python is me driving to the airport in the Prius, this is what you're doing trying to get to the airport, right? And so this is 120 times speed difference. And it doesn't have any space for the suitcase. So that would be an additional problem. So then you would think, okay, we've solved most of these problems, but now we have second generation problems. What are the second generation problems? So the second generation problems is that if one rack of FPGAs replaces 10 racks of CPUs, CPU vendors are selling 10 times less. That's a real problem. They've already predicted selling the CPUs forward for the next 10 years. They don't want to sell less, they want to sell more CPUs. So if the software could be made to run slower, that would be much better. They could sell more CPUs. And we don't, of course, have any examples where slower software is being put into advantageous positions to achieve that. Now, we build a cybersecurity product around this as well. We said, okay, you could build a firewall that's 10 times, 20 times smaller, faster, and more secure than a half a rack of commercial data center firewall today. They said, yes, that's great, but there's a commercial problem. We sell, I don't know, let's say if you sell 1,000 boxes at 1 million, that's $1 billion. If I can now reduce the cost of that box to 100,000, you're now only getting 10 million, right? But while you were getting a billion or 100 billion, while you were getting a million, while you get $1 billion before. So it causes just a drop in revenue right there because it is cheaper and faster, right? So cheaper and faster has real impact on commercial reality of companies. And even if they could, they wouldn't do it because it makes no sense to destroy your market where people are willing to pay $1 million to tell them, no, you can have it for 100,000. It's fine. That doesn't make any sense commercially. If FPGAs accelerate computation by 10 times, then the data coming out of that hits your infrastructure at 10 times the speed. Now you have to change all of your infrastructure to be able to deal with data coming at you at 10 times the speed. If the result of your computation is hitting a team of 10 people who has to read what the computation did and do something with it, if you accelerate the computation by 10 times, now the team of 10 people has to be a team of 100 people because you need 10 times more people to read the stuff that came out of the computation. And you could imagine other types of infrastructure. So the data velocity is increased. But the impact on the whole infrastructure can be catastrophic. If the FPGA solution means changing vendor, then of course the stability of your supply chain might be rocked. You might have relationships in place with a supply chain that goes all around the world. And because of one purchase of one computer, now your supply chain doesn't work anymore because it cuts across the supply chain. So you have to align with supply chains of people. If computing with FPGAs brings in language, there's a social problem. Maybe some people just don't like it. So we don't like Java. It's not a nice language. We only use this other thing. And then of course, there is a regulatory problem. If your computation uses a different type of arithmetic, you have qualified over a painstaking 10-year process, you've qualified a piece of code to be compliant with government requirements, and you've convinced the government to accept your computation as a fair computation to report to them, you've changed the arithmetic, now you have to start again. Try explaining to them how that works. Right? Take another 10 years. Who would want to do that? So these are all second-generation problems. And my conclusion here is really that the important thing is to think about the cycle, to think about the cycle of pain point, solution, conflict, which drives things in a circle, and spend more time enumerating and understanding these conflicts than actually solving them. Because if you just focus on solving them, every time you solve one, you just create a lot more of them. So solving less and analyzing the conflicts more seems to me at least to be a winning starting point, even though I don't have an answer to all the challenges posed here. It's just, again, an observation that I had, and I thought I'll share that. And that's the end of my talk. Thank you very much.
So So if the U.S. government is restricting Xilinx products going to China, how can you continue your project with Tsinghua?
I don't know. I have no idea.
Okay.
So the way, okay, so just to explain, there is a web page from the State Department which lays out on a day-by-day basis what US corporations are allowed and are not allowed to do. And you simply log on to the web page once a day, you look at what you're allowed to do, what you're not allowed to do, and you do that. And then you're okay. Right now, you're fine. Tomorrow, we do whatever it says.
Okay, fair enough. So just a related thing, it seems to me research inherently creates pain points. In fact, you could say it's the job of research to create pain points, because now you have to cope with these new discoveries and these new developments. Like right now we have this huge pain point in intelligent systems that the research community has gotten way out ahead, okay, of what the companies and the defense laboratories are doing, right? Mm-hmm. And so you worry about that because that creates a huge gap and somebody else might exploit it.
Yes. My point is to not worry about it, but to collect it. I find that there is a uncomfortableness in talking about conflict. People don't want to talk about conflict, want to avoid conflict, want to resolve conflict, but they don't want to make a list of all the conflicts possible that could happen. That is very socially unattractive. And I believe we need to step out of that and take on these conflicts and write them down in an impartial way, not taking sides, not trying to resolve them too quickly, but to collect them and think deeply about what all the different conflicts could be so that they don't come as a surprise afterwards.
We have this agency, DARPA, that's supposed to prevent surprise in the U.S.
Okay.
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 How are they doing?
I don't think that's what DARPA's supposed to do. Maybe somebody else has a problem.
Oh, all right.
Oh, over here.
So in companies' SEC filings, they have lots of risks. Right? Do you think those kinds of risks are related somehow to the conflicts that you're talking about that come out of technical solutions?
I think risk is different. I think we have a good handle on risk management. We have a chief risk officer in most large corporations. And I think we are dealing with risk in many, many different ways. There are professionals who deal with risk. And I find it is slightly different than conflict. Because conflict is not so much a risk as it is a status of things. It's not about what would happen, but just the fact. It's more about, maybe it's about what will not happen rather than what will happen. Risk is about the thing that would happen as a consequence of what you've done, while conflict is about the things that will not happen as a consequence of what you've done. Maybe that's an answer, I don't know. But it's definitely different.
Maybe risk is a probability of something happening, whereas conflict is the thing which might happen or might not happen.
That could also be, it could be probabilistic versus binary, absolutely. I don't know, yeah, it's an interesting question.
Oskar, yes. So you describe these problems and conflicts as if someone, has to solve them all themselves.
No, in fact,
the
it's
amount
the
of
opposite.
entropy, but they're like new smart people coming into the system, and sort of the amount of energy isn't to bring to bear on these problems is not really.
Yes. It is true that as a society, we have more and more people to tackle more and more problems. That's why I said my perspective is purely from an individual's perspective.
Yeah, but there's this a proverb that says if you want to go fast, go alone, but if you want to go far, go with a team.
Yes.
So it seems that this is a challenge for a diverse team
Yes.
of people to attack, and that's part of the initial problem, is
Yes.
putting together this team of people to attack this complex problem.
But in order to put together the diverse team of people, you need to be anticipating the type of conflicts that you might be getting in the future to have a team that can address these. So I fully agree, a team can help. And it's not just the addressing. I think the key is the speed at which you're addressing them, because you have to address them at a faster speed than they're coming at you. And the difference between a company that can scale up versus a company that stays flat or goes down is really the speed at which all of these different conflicts get resolved. So absolutely, in a global sense, you can look at it as a team of people resolving that. From an individual's perspective, even if you have a team of people, if the number of conflicts you're personally involved in is increasing, you need to deal with more and more of them. So you can't just increase the number of people you're talking to, because there's a limit to how many people you can talk to in a day. So there is a momentum balance kind of thing going on, where you need to deal with the conflicts faster than you're generating them.
Another question?
Thank you. So it sounds like one of the assumptions that we have is that as we solve pain points, we tend to generate them exponentially. But it seems like one of the other, I guess, halting solutions in the state that you put up in one of the slides would be if we can find some way of reducing the number of conflicts that are generated when we solve one. So do you have any tips for that, or what are your thoughts on that?
Well, in order to reduce the number of pain points that we are creating, we need to be able to think a few moves ahead. What I'm suggesting is that the chess player always thinks many moves ahead and has a tree of possibilities that they're going through. Right? You make a move, and then you have to anticipate the other side's move and anticipate the other side's move. If you read a book on product development, it does not do that. It does not go 2-3 steps out. And so that is what we have to develop. We have to develop a methodology to think several steps ahead and be able to think about how that would go. And it's getting harder and harder because, as I was suggesting, predicting gets harder and harder. But that's exactly what we need to do. We need to predict the things that we will be creating. In order to create less, right, we need to be able to first predict what will create. So you have 3 solutions you could go for. You need to be able to predict how many conflicts each one of these solutions would create, rather than just pick the one solution that is the least amount of work, which is the one that always gets picked, right? And the least amount of work may lead to most conflicts later on, but if you don't think, so thinking several steps forward in the cycle, drawing it as a cycle is the starting point, rather than a 2-step process where you say, you have a pain point, you have a solution, you're done. You need to think about the consequences and the consequences of these consequences, and then evaluate the options based on that. I think that's my suggestion.
Okay, can you explain how we can incorporate machine learning and the blockchain into this process? Anyhow, I think we're running out of time, Oskar. Thank you very much. It's a great talk.
Thank you, Dennis.